This is following directly on the heels of yesterday's work. Now, yesterday we saw to evaluate it algebraically, we had two methods. The first method was direct substitution, where I just take the 1 and I plug it in for t and see what that gives me. Although in this case, that would give me a 0 over a 0. That's what we call a bad thing. We cannot have 0 in the denominator, which means that I then am going to resort to the other method, which was to factor and cancel. So if you haven't yet, factor everything you can about this and then see where that takes you from there. Now for doing this factoring, a little hint for the top first. You see it starts with t to the 4th, but remember in many cases, a quartic like that will behave just like a quadratic. If this was t squared minus 1, I could factor it into two sets of parentheses, each one starting with a t. The only difference, because it's t to the 4th, is that it won't be t at the start of each. It's going to be t squared at the start of each. But it otherwise follows the same factoring techniques as what you would with the quadratic. And of course, the bottom is a difference of cubes. That's remembering a rule. We actually touched on difference of cubes yesterday in our in-class work. If you don't remember that one, you might check back at our notes that we took yesterday. All right, so on the top then, if I were factoring t squared minus 1, it becomes t plus 1 times t minus 1. So in this case, it's going to be t squared plus 1 times t squared minus 1. On the bottom, difference of cubes. The first one is going to be t minus 1, because we're doing the cube root of the first term, cube root of t squared is just t, and the cube root of the second term, cube root of 1 is 1. And the sign here in the middle, that's the same one that we start with. All right, then from there, the signs on the inside of this part, they're all, well, at least in this case, they're all opposite from that. They're all going to be pluses. So it's going to be t squared plus 1t, that's just t, plus 1 squared, which is just 1. Now at the moment, it doesn't look like necessarily we have gained anything, because I don't see anything right now that's in the both top and the bottom. But do you see that there is one more level of factoring that we can do? There's something else you can factor down a little bit more, break it down a little bit more. All right, so we do that last step of factoring, which is to factor down the t squared minus 1. Remember, if it's a difference of squares, we can do it. The sum of squares, there's nothing to be done. That t squared plus 1 is as good as it gets. But the subtracting, we can do that. And so I break that down. Notice what that gained us. I now have a t minus 1 in both the top and the bottom that I can cancel out. And so if I cancel those, then my new limit as t is approaching 1 has the t squared plus 1 and the t plus 1 still in the top. And then in the bottom, it's just the t squared plus t plus 1. Now that we canceled, now we try the direct substitution again. So now take your 1 and plug it in for your t's over here. And remember, when you plug it in, that means we no longer write the limit at that step. When we plug it in, that's a lot of 1s, right? All right. So let's go ahead and just do that. So 1 squared plus 1, well, 1 squared is 1, plus 1 is 2. Okay, so that's going to be a 2 on the top times the 1 plus 1, which is 2. This is tough math now, isn't it? All right, and then 1 squared, 1 on the bottom, plus 1, that's a total of 3. 2 times 2 on the top is 4, so the whole thing ends up giving us 4/3. Which tells me then that, remember that when I first plugged in 1 up here, I was dividing by 0. There is no value. It's not in the domain. But I did actually find a limit there. So what that's telling me then also is that if I were making this graph, that I would have a hole in my graph here, and that hole would be located at the point 1, 4/3. There would be a hole in my graph right there. And that's what that's really meaning there. Because, of course, if there's a limit from both the left and the right that's the same, but no value there, that can only be because there's a hole, not an asymptote. Now this first one, this was just practice with what we did yesterday. We got to learn a couple more rules today. And so to get us ready, I would like you to please rationalize this denominator. Now, of course, the first thing you have to remember is what it means to rationalize the denominator. So if you're fuzzy on the wording, basically get the square root out of the bottom of the fraction. Now, how we do that? You might be tempted to multiply by that same square root of x plus 1. But unfortunately, that won't quite work. Because if you did that, you'd have to multiply this by it, yes, which would get rid of the square root there. But I'd also have to multiply the 9 by that same square root. And I'd still have a square root in the bottom. That would not help us. So the trick here is remembering that in order to be able to get rid of the radical out of the denominator when we have a sum or a difference in the denominator, is we multiply by the conjugate. Now the conjugate meaning it's the exact same thing, so the 9 and the square root of x plus 1, except we flip the sign in the middle. So instead of doing subtraction, it's going to be addition. And of course, what I multiply on the bottom, I also have to multiply into the top of the same fraction. Now, why do we multiply by the conjugate? Well, I'm going to go a little abstract on you. If I multiply, actually let's stick with that one, a minus b times a plus b, and I multiply that out. Remember that that would give me a squared minus b squared, because I'd have a plus ab in the middle and a minus ab in the middle, and they would add to 0. They would go away. And so when you multiply two conjugates like this, basically all I need to do is square that first term and square the second term of my binomial. Now what's that look like in this case? It means that in the denominator of my fraction, I'm going to be squaring the 9, which is 81, and then I'm going to be subtracting the square root of x plus 1 squared. Well, of course, if you square a square root, it cancels out the square root, so it's just leaving us with the x plus 1. Be careful, though. If you write it like that, you've made a mistake. Remember that we are subtracting that whole thing, so put parentheses around it. Okay, well, that's the bottom. What about the top? Well, the top is just going to be 5 times 9 plus the square root of x plus 1. I didn't say the top would be prettier because of this. I just said we'd rationalize the denominator. Last thing you'd do is just clean it up. Like I might go ahead and distribute in the 5 on the top. Strictly speaking, I don't have to, but I kind of want to here. But then on the bottom, well, 81 minus 1 gives me 80. So the bottom just becomes 80 minus x. This would then be a rationalized denominator. The whole key to this, remember, though, was that whole idea of multiplying by the conjugate. That's what we're looking for. And that's actually going to be a very useful tool today as we go forward. Because our third method, which we're going to add to our notes now, for finding limits algebraically, is to multiply by the conjugate. And we'll see an example problem about why that is here in a moment. But first, add it into your notes. And so that method is going to be what we're going to end up using here. And so we're going to work through this one together here, using our new method. And yes, we do need to use the new method. Notice if I took the 0 and plugged it in for t right at the start, I'd be dividing by 0. And we cannot divide by 0. Therefore, I need some other way to modify the equation. And so first of all, you'll notice that there's no factoring that we can do. So the factor and cancel method doesn't work. Usually I take these in order. I start by trying to just use direct substitution. That didn't work. Then I try to factor if there's anything that can factor, and it can't. Then I'll resort to actually having to multiply by the conjugate, which is what I now need to resort to on this one. And so the conjugate is, multiplying by the conjugate is used to get rid of the square root wherever it currently is. So in this case, I'm going to multiply the top by the conjugate. And so I'm going to be multiplying the top in this case by the square root of t squared plus 9. Notice that stays a plus 9 in there. This is not the conjugate piece. The conjugate piece comes between the square root and the 3. That's the addition or subtraction that we're flipping. And of course, on the bottom, I have to multiply by the same thing, right? All right, so seeing that that is what we are doing, now go ahead and do that multiplication so we can check that we got that multiplying part down. So this is what your new numerator should be when you multiply by the conjugate. Make sure you got that, and then simplify from there, of course. And at first it seems like we haven't really gained much, because having multiplied by the conjugate, I now would look to see, can I plug in 0 for t, and I'm still going to be dividing by 0. But notice what it did bring up. There's actually a little bit of canceling we can do. So notice that after we multiply by the conjugate, we factor and cancel. In this case, I see a t squared on both the top and the bottom that's going to be canceling out. And so notice that when we cancel out the t squareds, we're left with just a 1 on the top. Now that I've done the canceling, now I try to do the direct substitution again. Good question. Why is the square root just of t plus 9 instead of t squared plus 9? Because I forgot to write it. Thank you. All right, good. Now let's go ahead and plug in from there. So we're going to take our 0 and we're going to plug it in for t in that expression. Remember, when I plug it in there, I no longer write the limit. I get rid of the limit notation when I plug in, and only when I plug in. And so you should end up with then a final answer of 1/6. I'd now like you to do one of these on your own. So please go ahead and now evaluate this limit. All right, and then we work it all through. We plug the 5 into our simplified version. And once we plug the 5 in for the x's here, we just calculate it down. We find out that we get 10 over 8, or actually reduce it, 5/4, or 1.25 if you prefer. Now, one little thing, but going back to the start, did you actually check direct substitution and see if that would work? I hope you did. I want you in the habit. I know we were just talking about we multiply by the conjugate, but get in the habit of it, starting by saying, okay, if I plug in 5, will that make me divide by 0? And yes, it did in this case, which is why we had to do that. But there will be cases where it looks like you have to do all of this work, and you really don't. You could just use direct substitution. So I just want you aware of that fact and kind of building that habit to always be checking that still. All right, next up, we're going to be taking a look at our last method for finding limits algebraically, which is to combine fractions. Go ahead and add this into your notes. And then go ahead and write down this problem, as this is the one that we're going to do as practice of this combining fractions method. Now when we talk about combining fractions, we're talking about doing the addition or subtraction of them, basically. And so for this one, well, before we get started, can we do the direct substitution? Will that work if I plug in 0 for x? No. We divide by 0. Okay, so that can't be done. So then, yes, that tells me I got to use another technique like combining those fractions. So I'm going to add them. In order to add them, that means I need a common denominator. So rewrite both of those fractions on the top with a common denominator, please. Once you get that common denominator, the whole point of doing so is so we can actually do the addition. So at this point, go ahead and take it from there, add those two fractions. And at this point, you hopefully start seeing why we did it. Because you'll notice that there's a little bit of reducing we can do in this. Hopefully you see it right away. If not, just kind of bring it out to the side and show. I'm taking this x over 2x minus 2, and I'm dividing it by x. Well, remember, division when we're dealing with fractions, division is the same as multiplying by the reciprocal. So instead of thinking it as divide by x, I can think of it as times 1 over x. And if I do that, I can see that that x on top and that x on bottom are going to cancel out. Or you could have just looked over here and said, okay, I got an x on the top, and I'm dividing it by x there. Either way, it's going to get you to the limit as x is approaching 0 of 1 over 2 times x minus 2. If you wrote that as 2x minus 4, that's perfectly fine. I just chose to leave it in factored form. All right, now that we did that, now that we combined the fractions, what's the point of doing that? Now try direct substitution. Now plug the 0 in for x and see what that gives you. And so when all said and done, you should get an answer of negative 1/4. And so notice what the combining the fractions did, is it manipulated our expression once again. And that's basically all we're doing with these two methods today, is manipulating our expressions to be able to hopefully find something that will cancel out. And when you do these, then be looking for, when can I see something that will cancel out along the way? Because I'm doing this to change the look, but it's in order to be able to find things that will cancel and make your life easier.